of the feature selection stage is to obtain a feature vector which can represent the entire database in a unique manner. Particle swarm optimization, formulated by Kennedy and Eberhard based on swarm behavior of bees and bats, is one of the ways to achieve this. Here, the video presents a simulation of the PSO algorithm. The particles utilize information from their neighbors and the best particle to converge to one best solution, the best particle being the one which represents the best solution at that instant. A binary version of the PSO is utilized to achieve a vector representing the best feature subset in face recognition. It runs iteratively to narrow down to the best solution. To obtain this, we initialize a certain number of particles with a position vector. Now, what is position? Each image of the database can be represented in a single dimension vector with certain values which are dependent on the brightness of each pixel. The particle's position is a vector which consists of ones and zeros, where 1 represents the corresponding feature being selected and 0 otherwise. The orange color means the feature has been selected for the iteration in progress. Also, each particle is initialized with a velocity vector. Now, what is velocity? The velocity vector contains values which represents the probability of a position vector value changing from 0 to 1. A new position vector is obtained by comparing the velocity value with the random vector. Similarly, every particle is initialized. Next, we have the iterations loop. Here, every particle's position is evaluated to test if it could be the best solution with the help of the fitness function to get a fitness value of that particle called the cost. The means of estimating this value is to calculate the class separation between the total mean array and the class mean arrays, where class mean array represents the average of each subject's images and the total mean array represents the average of all subjects' images. The particle is now assigned a cost. The color represents the value of the cost. Now, in one iteration, the particle with the highest cost is the global best particle, and its position vector is called the global best position. Also, each particle has a local best value, which is that particle's best possible solution. For future iterations, the velocity of each particle is evaluated based on the global best position and the local best position of it. The new velocity vector gives rise to a new position vector as discussed earlier, and the process follows. The proposed system utilizes the fact that each global best particle contains a different position vector. We use this information to calculate the weight array at every iteration. The weight values represents the aggregate of successive position values. When this weight array information is utilized to calculate the fitness function, a higher cost called the weighted cost is generated. This makes class separation better, which results in a better global best position that represents the best possible solution.